Welcome to Section 7, Lesson 6. In the previous lesson, we learned polynomial long division as the polynomial extension of integer long division. Today, we cover synthetic division, which is a fast shorthand for the special case where the divisor is linear of the form x minus c. The shorthand uses just the coefficients of the dividend without the variable letters organized in a compact tableau and produces the quotient and remainder in just one pass through the coefficients. Synthetic division is dramatically faster than full long division, perhaps 4 or 5 times faster on the same problem, but it only works for linear divisors of the form x minus c. Today we lock in the synthetic division algorithm, the tableau setup, and the connection to polynomial long division. First idea on the board, the synthetic division tableau setup. To divide a polynomial of degree n by x minus c, write the coefficients of the dividend across the top of a tableau in descending exponent order, including 0 placeholders for any missing exponents. Write c at the left of the tableau, separated by a vertical bar from the coefficients. Below the row of coefficients, leave a blank row, and below that, draw a horizontal bar with a bottom row beneath it for the running results. The tableau encodes the long division algorithm in a compact form that uses only the coefficients. Second idea, the synthetic division algorithm itself. Step 1, bring down the first coefficient of the dividend into the bottom row, unchanged. Step 2, multiply the bottom row entry by c and write the product in the middle row under the next coefficient. Step 3, add the column entry c top coefficient plus middle product and write the sum in the bottom row. Step 4, repeat from step 2, multiplying the new bottom row entry by c until all columns are processed. The final entry in the bottom row is the remainder. The earlier entries, read left to right, are the coefficients of the quotient polynomial, which has degree 1 less than the dividend. Third idea, connection to long division. Synthetic division is mathematically equivalent to polynomial long division when the divisor is linear of the form x minus c. The tableau condenses the multiply and subtract steps of long division into multiply and adds steps by absorbing the negative of c into the multiplication. The result, dividend equals quotient times divisor plus remainder, is identical to what long division produces. Synthetic division does not work when the divisor is not linear or when the leading coefficient of the divisor is not 1. In those cases, fall back to long division. Today, we drill the synthetic division mechanic on 2 examples and lock in the shorthand for the rest of Section 7. Synthetic division is a fast shorthand for polynomial division when the divisor is linear of the form x minus c. The algorithm uses only the coefficients of the dividend, no variable letters, organized in a compact tableau and processed in one left to right pass. Tableau setup. Write c at the left, separated by a vertical bar. Across the top, write the coefficients of the dividend in descending exponent order, including 0 placeholders for any missing exponents. Below the coefficients, leave a blank middle row for products. Draw a horizontal line, and below it the bottom row will hold the running sums and the final remainder. Algorithm. Step 1, bring down the first dividend coefficient unchanged into the bottom row. Step 2, multiply the bottom row entry by c and write the product in the middle row under the next coefficient. Step 3, add the column s top plus middle and write the result in the bottom row. Step 4, repeat steps 2 and 3 until all columns are filled. The final bottom row entry is the remainder. The earlier bottom row entries, read left to right, are the coefficients of the quotient polynomial. Result interpretation. If the dividend has degree n, the quotient has degree n minus 1. Read the bottom row entries except the last as the coefficients of the quotient in descending exponent order. The last entry is the constant remainder. The full division statement is dividend equals quotient times the quantity x minus c plus remainder. Restrictions. Synthetic division only works when the divisor is linear of the form x minus c. It does not work when the divisor has degree 2 or higher. It does not work when the divisor's leading coefficient is not 1, unless the divisor is rewritten in the required form first. For non-linear divisors, fall back to polynomial long division from the previous lesson. Today we drill the synthetic algorithm on 2 worked examples and lock in the shorthand for the lessons coming up. Here is the first worked example. Divide the polynomial 2x cubed plus 3x squared minus 8x plus 4 by x minus 2 using synthetic division. This is the same dividend and divisor as the long division example from the previous lesson, so we can compare the results directly. Step 1. Set up the tableau. The divisor is x minus 2, so c equals 2. Write 2 at the left of the tableau. The dividend coefficients in descending order are 2, 3, negative 8, 4. No missing exponents, so no zero placeholders needed. Write the 4 coefficients across the top of the tableau. Step 2. Bring down the first coefficient. The first coefficient is 2. Bring it down unchanged into the bottom row. Bottom row so far 2. Step 3. First multiply and add. Multiply 2 times 2 equals 4. Write 4 in the middle row under the next coefficient 3. Add 3 plus 4 equals 7. Write 7 in the bottom row. Bottom row so far 2, 7. Step 4. Second multiply and add. Multiply 7 times 2 equals 14. Write 14 in the middle row under the next coefficient negative 8. Add negative 8 plus 14 equals 6. Write 6 in the bottom row. Bottom row so far 2, 7, 6. Step 5. Third multiply and add. Multiply 6 times 2 equals 12. Write 12 in the middle row under the last coefficient 4. Add 4 plus 12 equals 16. Write 16 in the bottom row. Bottom row complete 2, 7, 6, 16. Step 6. Read off the result. The bottom row has 4 entries. The last entry is the remainder, 16. The first 3 entries, read left to right, are the coefficients of the quotient. The quotient is 2x squared plus 7x plus 6. Comparing to the long division example, we get exactly the same quotient and remainder, but with much less work. Synthetic division is roughly 4 to 5 times faster than full long division on this problem. So the quotient is 2x squared plus 7x plus 6 and the remainder is 16. The big lesson from this example is that synthetic division gives identical results to long division while requiring far fewer steps. The trade-off is that synthetic division only works for linear divisors of the form x minus c. For any linear divisor in this form, synthetic is the preferred method. Here is a second worked example, this time with 0 placeholders for missing exponents. Divide the polynomial 3x to the 4th minus 5x squared plus 7 by x plus 3 using synthetic division. The divisor is x plus 3, which we rewrite as x minus negative 3 to identify c equals negative 3. Step 1. Set up the tableau. The dividend coefficients with placeholders are 3, 0, negative 5, 0, 7. 5 coefficients total for a degree 4 dividend. Write negative 3 at the left of the tableau, separated by a vertical bar. Write the 5 coefficients across the top of the tableau. Step 2. Bring down the first coefficient. Bring down 3 into the bottom row. Bottom row so far 3. Step 3. First multiply and add. Multiply 3 times negative 3 equals negative 9. Write negative 9 under the next coefficient 0. Add 0 plus negative 9 equals negative 9. Bottom row so far 3, negative 9. Step 4. Second multiply and add. Multiply negative 9 times negative 3 equals positive 27. Write 27 under the next coefficient negative 5. Add negative 5 plus 27 equals 22. Bottom row so far 3, negative 9, 22. Step 5. Third multiply and add. Multiply 22 times negative 3 equals negative 66. Write negative 66 under the next coefficient 0. Add 0 plus negative 66 equals negative 66. Bottom row so far 3, negative 9, 22, negative 66. Step 6. Fourth multiply and add. multiply negative 66 times negative 3 equals positive 198. Write 198 under the last coefficient 7. Add 7 plus 198 equals 205. Bottom row complete 3, negative 9, 22, negative 66, 205. Step 7. Read off the result. The last entry of the bottom row is the remainder 205. The first 4 entries are the coefficients of the quotient 3, negative 9, 22, negative 66. The quotient is 3x cubed minus 9x squared plus 22x minus 66. Verify by multiplying back the quotient times the divisor plus the remainder should equal the original dividend. So the quotient is 3x cubed minus 9x squared plus 22x minus 66 and the remainder is 205. The big lesson from this example is that the synthetic division algorithm scales mechanically to any degree, including dividends with missing exponent terms via zero placeholders. The pattern of multiply and add stays identical regardless of the polynomial size. 3 mistakes that catch every algebra student during their first weeks of synthetic division work. Each one is fixable with a small explicit habit applied on every problem from now on consistently. First mistake, getting the sign of C wrong. A student looks at the divisor x plus 3 and writes C equals plus 3 at the left of the tableau when actually C equals negative 3 because the divisor must be rewritten in the form x minus C. Plus 3 would be correct only if the divisor were x minus 3. The fix is to always rewrite the divisor explicitly in the x minus c form before extracting c, and to be careful about the sign 3px plus 3 becomes x minus negative 3, so c is negative 3. Sign errors on c corrupt the entire tableau computation. Second mistake, skipping zero placeholders for missing exponents. A student tries to synthetic divide 3x to the fourth minus 5x squared plus 7 by writing only 3 negative 5, 7 across the top of the tableau, omitting the zero placeholders for x cubed and x. The number of bottom row entries comes out wrong, and the resulting quotient is corrupted. The fix is to always insert explicit zero placeholders for every missing exponent, exactly as in long division. Zero placeholders are mandatory in both algorithms. Third mistake, trying to apply synthetic division when the divisor is not linear. A student attempts to synthetic divide by x squared plus 1 or by 2x minus 3 when synthetic division only works for divisors of the form x minus c with leading coefficient 1. The fix is to always check the divisor before starting. If it has degree 2 or higher, fall back to polynomial long division. If the divisor has leading coefficient not equal to 1, but is still linear, factor out the leading coefficient first to put it in standard form. Apply synthetic only when the divisor matches the strict shape requirement. Synthetic division shows up across the remainder theorem, factor theorem, root testing, and polynomial reduction continuously. 4 broad sectors below where every algebra and beyond practitioner uses synthetic division as the workhorse polynomial evaluation tool. In the remainder theorem of the next lesson, we prove that the remainder when dividing p of x by x minus c equals exactly p of c, the value of the polynomial at c. This means synthetic division is also a fast way to evaluate polynomials at specific values. Just synthetic divide by x minus c and read off the remainder. Synthetic division evaluation is much faster than direct substitution for high-degree polynomials, and it shows up continuously in numerical analysis and computer algebra. In the factor theorem of the next lesson, x minus c is a factor of p of x if and only if p of c equals 0. Equivalently, the remainder of synthetic division by x minus c is 0. Synthetic division therefore directly tests whether a candidate is a root of the polynomial, and if so, simultaneously produces the quotient polynomial of one lower degree. Combined factor checking and degree reduction is one of the most useful applications of synthetic division. In rational root theorem testing covered in Lesson 9, candidate rational roots are tested by synthetic division with c equal to each candidate. Roots produce zero remainder, non-roots produce non-zero remainders. The candidate testing is fast because each test is just one synthetic division pass, and modern algebra software libraries use exactly this approach for symbolic root finding. In polynomial root reduction, once a single root c has been found, dividing the polynomial by x minus c using synthetic division produces a quotient polynomial of degree 1 less, whose roots are the remaining roots of the original polynomial. Repeated find a root and divide it out is the standard approach for finding all roots of a polynomial, and synthetic division makes the divide it out step essentially free in computational cost. 3 things to take with you from this lesson today. Synthetic division is the fast shorthand for polynomial division when the divisor is linear of the form x minus c, and it is the workhorse evaluation tool for polynomials in algebra, calculus, and computer algebra. First, synthetic division uses only the coefficients of the dividend, no variable letters, organized in a compact tableau processed in one left to right pass. Set up right C at the left of the tableau, the dividend coefficients across the top in descending exponent order with 0 placeholders for missing exponents. Then bring down the first coefficient unchanged, multiply by C, add to the next coefficient, and repeat across the row. Second, the result interpretation. The last entry of the bottom row is the remainder. The earlier entries, read left to right, are the coefficients of the quotient polynomial, which has degree 1 less than the dividend. The full division statement is dividend equals quotient times the quantity x minus c plus remainder, exactly the same as long division produces. Synthetic and long division are mathematically equivalent for linear divisors, but synthetic is roughly 4 to 5 times faster. Third, restrictions. Synthetic division only works for divisors of the form x minus c with leading coefficient 1. It does not work for non-linear divisors or for linear divisors with leading coefficient different from 1. For non-linear divisors, fall back to polynomial long division from the previous lesson. For linear divisors with non-unit leading coefficient, factor out the leading coefficient first to put the divisor in standard form. Coming up next, the lesson called Remainder and Factor Theorems, which builds the theoretical foundation underneath synthetic division. The remainder theorem says P of c equals the remainder of dividing P of x by x minus c, and the factor theorem says x minus c is a factor of P of x if and only if P of c equals 0. Both theorems make synthetic division essential for polynomial evaluation and root finding.